let's calculate some Gibbs free energy values here. So if you remember from the last video, I mentioned that we could do the exact same thing that we did with enthalpy and with entropy. We can do that with Gibbs free energy values as well, standard Gibbs free energy values. So let's go ahead and practice doing that. Hopefully you have your book out with the appendix open so you can work along with me. So we are given an equation here. It says the ozone in the lower atmosphere is a pollutant that can form by the following reaction involving the oxidation of unburned hydrocarbons. So we have methane plus oxygen goes to carbon dioxide, water, and ozone. Use the standard free energies of formation to determine delta G for this reaction at 25 degrees C. So this one would be a huge pain if we did it the same way that we did the last problem that we worked through, because we would have to find 5 different delta H values, most of them with coefficients to take into account, 5 different delta S values taking their coefficients into account, and it would take 10 minutes just to physically write the whole thing out. So instead, we are just going to do one calculation here using delta G values instead of delta H and delta S values. So notice the units on the delta G values in the table, because I'm going to leave the units out again here, but they are kilojoules. Ew, sorry, that's kind of scrunched in the corner there. Kilojoules per mole are the units on delta G. And again, those mole values are going to go away because we're multiplying by the coefficients. So we're going to have our products minus reactants. So we're going to put our products here first. We have 3 of those. I'm just going to go ahead and start from the right and work my way towards the left. So we're going to have 4 times the number for ozone, which if I go back to oxygen, let's see, there's ozone. So delta G value for ozone is 163.2. That is a positive value. So I'm going to add to that 2 times the number for gaseous water, which is negative 228.6. And then I'm going to add to that 1 times the number for CO2. So I'm just going to leave the 1 out. So CO2 in the gas phase, if I flip over to carbon, CO2, where are you? There you are. Okay. So CO2 in the gas phase, negative 394.4. Alright, so those are our products. So again, products minus reactants. So we have 8 O2. If you find oxygen on the table and you look at O2, what you will find is that delta G for O2 is 0. So we have 8 times 0, which is just going to be 0. And then we will have 1 for CH4. So if we go back to carbon here, CH4 in the gas phase is negative 50.5. Alright, so if we do that sum, so 4 times 163.2 plus 2 times negative 228.6 plus negative 394.4, all of that is going to end up being all of that plus 50.5, since we're subtracting a negative number. Delta G for this reaction is negative 148.3 kilojoules. So again, that per mole goes away since we're multiplying by the number of moles in the coefficient. Alright, hopefully that made sense. And hopefully you can see how that is so much shorter than doing it the way we did back here, where we had all we had three different equations essentially instead of just one. There is another way to find delta G values. If you remember back from General Chemistry 1, we had an alternative way for finding enthalpy values for reactions. Because enthalpy is a state function, and delta G is also a state function, by the way. Because enthalpy was a state function, we were able to add reactions together. So if we had multiple different reactions, we could add them together to make the reaction that we wanted. And if we could do that, if we could add those reactions together to get the reaction we wanted, we could do the same thing with their delta H values. So we could add the delta H values to get what we wanted. And we would accomplish that by flipping reactions backwards from the way they were written, and we would just have to flip the sign on delta H, and we could multiply everything in the reaction by a integer value, and then we would just multiply the delta H value by the same integer. We can do that exact same thing with delta G values. If you remember from Chem 1, we called that Hess's law, I believe is the name. This is not technically called Hess's law, but it is essentially the same thing as Hess's law. And so what that allows us to do is something like this, where we have three different reactions. And if we can manipulate these to get the reaction we want, doing the exact same manipulations to the delta G values will give us the delta G that we want. So we are trying to find delta G for this reaction. And so the method that I always use when trying to solve these types of equations is see if there's something that I need in my goal equation that only shows up in one place in the possible reactions that I have. So, for example here, I need 3 carbons on the left side of the reaction. Carbon, all by itself, only shows up here. There's no pure carbon anywhere else. So, I need to then take this equation and multiply it by 3, which would give me 3 carbons plus 3 O2 goes to 3 CO2. And I'm going to do the same thing to its delta G value. So it would be 3 times negative 394.4. H2 only shows up in one place. It shows up here. I need 4 H2s on the left, and I only have 2 in this reaction as it's written. So I'm going to need to multiply everything here by 2. So I'll end up with 4H2 plus 2O2 goes to 4H2O. So I'm going to multiply this by 2 as well. So it'll be 2 times negative 457.1. And then I need 1 propane on the right. I have propane in this reaction, but it's on the left. So I'm going to need to flip this thing. And by flipping it, I'll end up with 3CO2 plus 4 waters on the left goes to 5 O2s plus C3H8. And then I'm going to flip the sign on delta G. I'm not going to take the reciprocal or anything like that. I'm not multiplying by anything because I didn't multiply this by anything. I just flipped it. And so it's going to be positive 2074 instead of negative. So if I add these together and I get the equation I want, I will also be able to add these together to get the delta G that I want. So when I add these together, what I'm looking for is I'm looking for anything that cancels out. So for example here, I have 3 CO2 on the right and 3 CO2 on the left sides of the equation. Those cancel each other out. It's just like a mathematical equation. If you have the same thing on both sides, they cancel out. Same thing here with the water. 4 waters, 4 waters. At first glance, it doesn't seem like the water works out, but if you look, I have 3 plus 2, sorry, not waters, oxygens, on the left, and I have 5 oxygens on the right. So those do actually cancel out. And so I'm left with 3 carbons plus 4H2 goes to C3H8, which is indeed the equation that I'm trying to make. And so because I can add the equations together to get the equation that I want, I can also add the delta G's together to get the delta G that I want. And so if I do that real quick, 3 times negative 394.4 plus 2 times negative 457.1 plus 2074 gives me negative 23.4 kilojoules. So that is the delta G value for that reaction. Now, thankfully for you, I am much more interested in having you do delta G values this way. I'm using standard values from the table. I'm much more interested in that than having you do it this way. But I did want to still show you that it could be done. It is just like enthalpy. You can actually take multiple equations, add them together, and get the equation that you want. But I think this is kind of tedious and not nearly as useful as just why would I look for multiple equations that when added together give me the equation when I want when I could just go to a table and get 3 numbers and be done. So I'm much more interested in you being able to do it this way than do it this way. But you should still know that it can be done, and you should still be capable of doing it, since it is just exactly the same thing as what we did in Chem 1 with enthalpy values. Alright, we're going to call it there for this video. In the next one, we're going to talk about how we can relate equilibria to the Gibbs free energy, and how we can not only relate just equilibria in general, but specifically, we're going to talk about actually relating the equilibrium constant to the Gibbs free energy value.